Please send your homework for 3-1 to your left. All in all, I'm not unhappy with the exams. If there's a note on your exam about talking to me, please come talk to me. Other than that, I posted the key yesterday after I finished grading. Take a look. If you've got questions, come talk to me. I'll go from there. A lot of what we do in linear algebra revolves down to working with matrices and vectors. But what I really want to do is abstract those ideas a little bit. I like working in Rn. It's easy. But there are lots of other collections of things that I can use as vectors. As long as I make sure that they behave in the same way. The hell does that mean? All right, well, that means I can define a vector space. I'm going to take any set of things V. I'm going to define for them two operations, the operation of addition, where I add two things in the set, and the operation of scalar multiplication, where I multiply one of the things in the set by a scalar. A scalar is a number. For our purposes, it is a real number. It could be a complex number. We could only be working with integers. So it depends on what we're working with as to what kind of scalars are allowed. I'm leaving it vague at the moment. The list of properties is on the very first thing in section 4.1. There are 10 properties. You don't have to memorize them. You're welcome to just say, hey, look at the book for the 10 properties, but I want to go through this. The first 5 are all about the addition idea. If I add two things in my set, I stay in my set. We refer to this as closure of the operation of addition. So when you add two vectors, you stay with the same kind of thing. Notice this doesn't work for all sets. What happens if you add two odd numbers? I don't get an odd number, I'm not in the same set. So the set I choose matters. I want the commutative property. So it doesn't matter what order I do the addition in. I want the associative property. So if I add more than two things, it doesn't matter which pair of them I add first, u plus v and then add w, or add v and w first and then add u. Those are equivalent. It's the associative property. I want there to be an identity element for addition. Number 4, there exists a thing I will call 0 in the set V so that u plus this 0 thing is again u. So there is an additive identity. And as soon as I have the idea of identity, I want to have the idea of an inverse. For every vector, there is an opposite vector that gets me to the 0 vector. All 5 of these relate to our addition property. I want similarly defined properties for multiplication. So when it comes to the multiplication part, I want to say that if you multiply by a scalar, you don't leave the set. This is closure again, but this time it's of the other operation. I want distributive rules, but I want 2 different kinds of distributive rules. I want to be able to distribute a scalar over 2 vectors. That makes sense. I want this thing to kind of behave linearly. And I want to be able to distribute 1 vector over 2 scalars. I also want to be able to associate multiplying so it doesn't matter whether we multiply the 2 scalars first or multiply the scalar by one of the numbers first. And then the last property is the identity property for multiplying. Multiplying by 1 doesn't change your vector. That is a huge ass list. But any set of things that obeys all 10 of these rules is a vector space. All of the vector spaces we've been dealing with, Rn, works perfectly here. That is my prime example of a vector space, is Rn. But here's another option. This is a funky looking S, like we had the Z and the R for real numbers and integers. This S is for sequences. And these are doubly infinite sequences, so I will often write something like xk, where k goes from minus infinity to infinity. That should look kind of like a sum from Calc 1, where we did the Riemann sum things. Only this time that k is our index. It's a loop, basically. Go through and list the numbers from negative infinity to infinity, and that's my setup. Now, I don't tell you what these things are. They could all be 1s and 0s. They could be real numbers. They could be integers. It depends on what scalars I want to use. But if I have these things, then I need to have the 2 operations. I need to know, how do you add sequences? How do you multiply a sequence by a scalar? Let's try that again. xk plus yk is add each corresponding entry. And multiplying by a scalar means you multiply every single entry in the sequence by that scalar. What the actual? Imagine you are listening to the radio, to a singer, to a bird, whatever, and every millisecond you record a note. What frequency is that note? Right now, right now, right now, right now. That's this sort of signal. It's called a discrete time signal. And what you're really doing is creating what looks like a pulsed version of a sound. If I listened to a recording and I said, okay, and I asked you every millisecond to tell me what note I was whistling, you might get something that looks like this. As the frequency goes back and forth, the vibration, right? That's what I would see, but I wouldn't see a smooth wave. I'd see all these distinct separated dots. That's the discrete part of it. As I count, K is 0, K is 1, 2, 3, 4, 5, 10. Here are the negative ones. I didn't start until time 0 in this case. But here's a type of a signal. And it looks like the graph of some function, but it's not smooth. It's just a bunch of dots. I claim all of these things are true for this collection. If my goal is to add 2 of them, and I do that by adding the entries, does it matter what order I add those numbers in? Well, that means that adding the signal x to the signal y is the same as adding the signal y to the signal x. That was property 2, right? The commutative rule. I can go through by hand and do the algebra to show you that all 10 of these properties are going to be true. I don't want to, but I could. Here's another set. The set of polynomials of degree at most n. What's the degree of a polynomial? What does that mean again? The internet is your friend. Look up degree of polynomial. It is the highest power. So I would say I want a polynomial whose highest power is at most n. And I want to use the same rules we use throughout all of algebra and all of calculus to add. P of x plus q of x, gather like terms, C P of x, multiply through all the coefficients. If I really wanted to be anal retentive about this, I'd write out 2 polynomials of degree at most n and show you how I add them. But you've seen that back in algebra class. You know how to add quadratics, right? All I'm doing here. So these are quote unquote the normal rules for algebra, and the normal rules still carry all 10 of those properties. That means the set of polynomials can be thought of as a vector space. Somehow that means there's a connection between quadratic equations, polynomials of degree at most 2, and arrows, 3-dimensional space. right? This is what a quadratic polynomial looks like. So if I were to say, what if I were to just give you a vector? Doesn't that automatically give you a quadratic polynomial? I gave you A, I gave you B, I gave you C. That's a particular quadratic, isn't it? It's going to be ax squared and bx plus c. There's no difference between me writing down this or writing down this. But I know how to add quadratics. Same as adding vectors, right? I add the things in the corresponding places. I gather all the like terms. I gather the x squareds, I gather the x's, and I gather the constants. I don't have to think about quadratic equations ever again if I like thinking about vectors instead. Even calculus was hiding these sorts of ideas. The set of functions whose domain is some open interval. I could use the interval minus infinity to infinity. I could use the interval from 0 to infinity. I could use the interval from 0 to 1. I could use any interval I want as long as the function I am looking at is defined in there. So something like 1 over x wouldn't make sense if I used the interval including 0. Something like tangent of x wouldn't make sense if I used the interval including pi over 2. So it's going to depend on what interval I'm looking at. But then this that's defined everywhere. E to the x is defined everywhere. Cosine of x is defined everywhere. X cubed is defined everywhere. So I have functions. And the rules of algebra that we use are exactly those same 10 properties we've already listed. How do you multiply e to the x by 2? Well, you just multiply all the y values by 2. How do you gather like terms? Well, I just combine whatever I can, right? If I've got 2 cosines, I'll glue them together. If not, I'll just stack them all up with plus signs between them. That's addition of functions. That's our operation of adding. It works perfectly. It is possible to use linear algebra ideas in hundreds of different places, which means ideas of linear transformations, our ideas of determinant, all of this linear independence idea should somehow get translated into these abstract spaces. I could spend the next several weeks saying, oh, well, let's look at this abstract space. Let's look at this abstract space. I just told you, I look at quadratic polynomials, I really see vectors that look like R3. If I know how to do stuff in R3, I know how to do stuff in quadratics. As long as I can figure out how to translate, I'll be good. So really, my first question is, do I have an actual vector space? When I present you with a set and a definition of how we're going to do the operations, I might make some weird change. And then the answer is, I don't know yet. How do we find out? That's when I have to go through and look at all these stupid properties and see, did any of them break? Here's an example. I am thinking of vectors with two entries, x, y, where x and y are both bigger than or equal to 0. And I want us to use the normal operations, the same vector adding and the same vector multiplying we've been using for 3.5, 4 weeks now. So here's my question. Do my properties all hold? My first reaction might be, you're using the normal operations, where would you have something up? If I change the adding idea, then I would want to look at adding. If I change the multiplication idea, I'd want to look at multiplication. What I changed is what defines a member of the set. I need to know if I stay in my set when I do things. That's rule 1 and rule 6. That's the closure idea. So let's start there. Tell me, if you take two things that look like this and you add them, will the result be something that looks like this? So, operation number 1 says if I have x1, y1, and x2, y2, we'll call those u and v, and I know all 4 numbers involved there are bigger than or equal to 0, and I add, what do I get? You get a vector with 2 things in it, right? I'm adding 2 vectors. What should the entries in this vector be? Now, in order to be a member of my set, this thing must satisfy this property. This thing must satisfy this property. Is that true? It absolutely depends on the numbers, but what do I know about these 4 numbers? So when you add 2 things that are greater than or equal to 0, your result is greater than or equal to 0. Perfect. Okay, so property number 1 works. What about property number 6? If the vector u is x1, y1, x1 bigger than or equal to 0, y1 bigger than, and c is any scalar. Remember, this has got to be true for every possible vector, for every possible scalar. What do I get when I do cu? In order to be part of my set, this must obey the rule. Does it? Why not, Brock? Ah, crap. If I let c be a negative number, that's not going to be positive, is it? One counterexample is all I need to prove that a universally quantified statement is false. Chapter 1, section 6, discrete. I knew I needed that stuff. All right, so here's an example of a space that, in spite of the fact that I wanted it to work, I found an axiom that was broken. I can't use it. By the way, there is a corollary to all of those axioms. When I multiply any vector by the zero constant, I get the zero vector. When I multiply any constant by the zero vector, I get the zero vector. And the opposite vector that I mentioned in, what was that, rule number 5, the additive inverse must be the same as -1 times the vector I come up with. Which, by the way, means if any of those are broken, one of my axioms has to be broken. Questions? Rather frequently, the vector spaces that math geeks like to work in are spaces of functions, spaces of matrices. The matrices themselves are the vectors we are using, which means I'm doing a transformation from one vector to another, becomes changing one matrix into another, like our row operations. The transformations that we will study on these kinds of spaces will be then related back to the transformations we knew on vectors already. So hopefully, my goal is to make our lives easier by thinking of all of these crazy spaces when they work as if they were Rn for the right kind of n. I just figure out how to do that. This last example, I said that we started with vectors with 2 entries in them, which means I already knew I was looking at part of R2, a subset. A subspace means I start with a vector space. And I say, okay, this is let's take a subset of that vector space, which is what I did. I want that to be a vector space on its own, using the same operations as I used in V. Since everything in H is also in V, I can do all of those operations I did in V on the things in H. Now you might think that that means I need to check all 10 of these axioms again, now using things in H rather than things in V. But 99% of the things that are in those properties are things that apply to everything in V, so they also apply to the things in H. The only three I need to be careful of are the two closures and the placement of 0. All right, wait a minute. To be closed means if I have two things in the space, then their sum is in the space. To be closed under multiplication means that whenever I do CH, I stay in H. And that was the property that was broken in our last example. Because as Brock pointed out, I could use the constant that was negative and then I'm not in the section I wanted to be in. It turns out that's all you have to check. You only have to check those three and nothing else. It turns out you've already seen an example of this that worked. The polynomials can all be thought of as functions. So polynomials are a subspace of functions, but there are functions that are not polynomials, right? Cosine x, e to the x, 1 over 1 plus x squared, those are not polynomials. So those are things that are in here that are not in the set of polynomials. The set of polynomials is a vector space unto itself that lives inside that set of larger functions. Here's a boring example. In any vector space, the subset that only contains 0, does that satisfy all three of the properties? Wait a second. 0 is definitely in there. That's property 1. Take two things from this set. Well, then they both have to be 0. When you add them, 0 plus 0 is 0. Isn't that in the set? Check, number 2. Take any constant you want and multiply it by the 0 vector. What do you get? That vector. You're in the set. It's boring. It's just a dot. There's only one vector there, but it satisfies all of my properties. So let's think about our set of time signals. Discrete time signals that we were looking at earlier. If every number in my infinite sequence is 0, that's the 0 signal, right? Your machine is off. Okay. No matter what you do to that signal, add it to itself, it's still 0. Multiply it by any number, it's still 0. You haven't turned the machine on yet, man. Nothing's going to change. Questions? I like the set of signals a lot. Signal processing and filtering and signal attenuation and all of that is actually a really deep linear algebra mathematics concept. Error correcting codes, transmission fidelity, all of that becomes linear. Let's create a new signal space. I will call it SF. SF is the set of discrete time signals that only contain finitely many non-zero entries. Excuse me for a moment. What the hell does that mean? I don't care how many, 100, 1,000, 73, there are only so many dots that aren't zero, right? That means there is a lowest entry dot that's non-zero and a highest entry dot that's non-zero. And everything outside of that is all zeros. We call these signals with finite support because they only exist between two finite values. I don't know what those values are, and each signal could have a different finite support. But each signal has a lowest non-zero entry and a highest non-zero entry. So the signal 0, 1, 0, 1, 0, 1, 0, 1, 0, 1 is not in here. That keeps going on and on forever. Is this a subspace of S? I am going to butcher that funky looking S over and over and over. I apologize in advance. The set S for the signals just is an atrocious letter in my handwriting. Okay, I need to check three things. What are the three things I need to check?
If it's 0 times your vector, is it still 0?
Not quite. That was the corollary. What's the theorem about being in a subspace or being a subspace?
The zero vector is part of it.
The zero vector is part of this. So let's start with that. 1. Is the zero signal in SF? How many non-zero entries are in the zero signal?
Many.
Well, sure, but it's an exact number. How many? There aren't any non-zero numbers, are there? 0 is definitely finite. That one works. That was property 1. There are 3. What's property 2? Closure addition. So let's give ourselves two signals, xk and yk. I don't know how many non-zero entries there are in X, but there's some number of them, right? So let's say there's that many. N1, some number. It could be 2, it could be 143, it could be 7,826. I don't care. What about yk do I know?
Supposedly be the same as whatever xk is?
I don't know that. All I do know is that it has some number of non-zero entries, right? And all I know about those two numbers is that they're finite. Now, here's the fun part. Some of those entries might line up with each other. Yes? Some of them might be the same. Some of them might be different, though. So xk might have a 0 where yk has a 7. And xk might have a 0 where yk has a 0. I don't know. But I do know that when I add, oh, and xk might have a 1 where yk has a negative 1. Which means when I add, I might get a 0 where I didn't have one before. What's one thing I can guarantee you cannot happen? Can't add 2 zeros, get something that isn't 0. Isn't n1 plus n2 still finite? Check mark. Smiley face number 2. What was property 3? Closure of multiplication. So pick one of those and multiply it by something. As long as you're multiplying by something other than 0, are you going to change how many things are not 0? Which means if this starts with n1 non-zero entries and you multiply by 7, all of those non-zero entries are now just 7 times bigger. They're still not 0. And that still means the number of them hasn't changed. And if n1 was finite to start with, it's still finite now. That's check mark, smiley face number 3. For the record, finitely supported signals are much more common than infinitely supported signals. Because when you listen to something, you start it and you end it, don't you? There's a piece of music called ASAP, which stands for as slow as possible. Kid you not, performing this piece of music will take over 600 years. They have been playing the last note, I think, over a decade now. It changed this month. That's still finitely supported, but damn! Questions? Packet transmission across internet protocols is finitely supported transmission. Useless people, all you CS people, never going to see this anywhere. TCP/IP, anybody? This is a sentence that unfortunately pisses me off. Because you might think that, well, two vectors should be contained in threes. But when you deal with R3, you're dealing with things that look like this. And when you deal with R2, you're looking with things that look like this. If you add two of these, you don't get anything that looks like this, do you? That fails to be closed. As a matter of fact, the 0 from R3 is nowhere to be found over here. But what I could do instead is I could say in R3, let's look at the set AB0. If you take two things that are in this collection and you add them, the third number is still going to be 0, isn't it? If you multiply by some scalar, the third number is going to be 0. If A and B are both 0, then I get 0, 0, 0, and that's the 0 vector I wanted. This is a subset of three-dimensional space. In our visual terms, remember we had x's and y's and z's? This is the space that is just x and y. It's the floor of the room. But that's not the same as the x and y space that doesn't have any z's in it at all. Suppose we have any vector space. We take some vectors, a handful of them. As a matter of fact, let's call the collection of vector space of vectors here, we're going to call that S for set. Then the span of S is defined to be a set of linear combinations of the things in that set. The span of a set of vectors is a subspace of the vector space it comes from. It might be the whole thing, like on the exam where I asked if the columns spanned R5, and they didn't because they were linearly dependent. We were missing a pivot. But that means that they made a subspace because there were 4 pivots. That subspace, whatever it is the subspace spanned by the columns, the subspace spanned by these vectors. If I can build a good set S that allows me to describe my vector space nicely, I get a better handle on that vector space. We did this with Rn by using the vectors E1, E2, E3, and so on. My goal is to try and figure out what the good examples are and what the good foundational handles can be. But run against the clock. Please, 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 examples 10 through 13 in this section, go through a lot of this for span very carefully. But you've seen this before. I will see you all on Wednesday. Have a wonderful rest of your day. Yes. Yep. I'm sorry? Yes. I don't want them back.